Now, let's start Kirchhoff's laws. Right now, keep in mind, Kirchhoff's laws are by order, so you should remember it, just like Newton's first law, Newton's second law. There's an order, right? So, what is Kirchhoff's first law? That is called current law, or also known as KCL. That's pretty simple, right? It basically says that the sum of currents entering a junction it's pretty basic. You already know this stuff. Junction is equal to the sum of currents leaving a junction. That's it. It's pretty basic, right? And by the way, keep in mind that this current law is based upon conservation of charge. Conservation of charge. Remember that. Okay. So the current law is associated with the conservation of charge. Now, what does that mean? That means, for example, if you have IT over here, then IT is going to split into I1 and I2, right? So notice that according to this, that if there is a junction over here, then that means that an equation connecting these two is that the current entering a junction is IT, then the current leaving the junction would be I2 plus I1, right? And over here, check this out. It is I2, it is I1 and I2 entering. So that means when they add it up, it should total equal to IT, right? That's pretty much it. You already know this stuff, right? Now, for example, how do I make an equation connecting these currents, right? So this is like inward, 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 outward. So just sum it up. What are the total currents entering the circuit? It is I1 plus I2 plus I3. They're all entering, and that should mean then I4 is actually equal to the sum of all of these, right? Because this is the current leaving and this would be the current entering. So all of them would equal to I4. Okay. Then let's check this out. Calculate sum of current in and sum of current out to figure out this current. Is Kirchhoff's first law satisfied or not, right? Now, first of all, notice what is the sum of current input or sum of current, uh, you know, entering the junction, right? So this is junction. So I think 2.5 enters, 1 enters, and 3 enters, right? So what is the total current input? 3 plus 1 plus 2.5, right? So that's going to be 3 plus 4, 6.5. Okay. Is that it? Yep. And how many currents are exiting junction? They are 4, 4.5, 6.5. So it's correct. So that means because the total current exiting the junction and the total current entering the junction is equal, so that means Kirchhoff's first law is satisfied. That's it. Kirchhoff's first law is pretty basic. It's easy, right? Kirchhoff's voltage law is the more important and tough one, right? Now, what does Kirchhoff's voltage law says? That's basically the same thing that we've already studied. This is based on law of conservation. I've already taught you this law, by the way. I'm just giving it a name now. Based on law of conservation of energy, right? How? We already know this, that if we have an EMF E with voltage V1, V2, V3 drops, then E should equal to V1 plus V2 plus V3. That's it, right? That's all there is on the law. So, sorry, on Kirchhoff's voltage law, right? If I were to define Kirchhoff's voltage law, that would be that the sum, I'm going to write it over here, that the sum of EMFs is equal to the sum of potential differences in a loop. This is what Kirchhoff's voltage law is. So remember this. I would recommend that you even write this down, in full form. Do not write it down as I've written it. Write down the full form, right? The sum of EMF is equals to the sum of potential difference in a loop and blah, blah, blah. Okay, so this is what Kirchhoff's voltage law is. Now, conservation laws, and by the way, Kirchhoff's voltage law is also known as Kirchhoff's second law. It's just like Newton's law, right? So, Kirchhoff's laws, you have two of them, KVL and KCL. KCL, This is a MCQ that pops up like every year, right? They tell you that upon which laws are KVL and KCL based upon. KCL is the current law. It is based upon the law of conservation of charge. KVL. KVL is based upon the law of conservation of energy, right? So D is the answer. KVL is based upon law of conservation of energy and KCL is based upon law of conservation of charge. Remember that, okay? In case you forget. Now, how to use Kirchoff's law in loops, right? So, pay very close attention. It might not immediately make sense, okay? But once you connect the dots, it will. So, remember this, by the way, right? Take this to the heart. Sum of EMFs is equal to sum of PDs in a loop. Okay, loop is important. In fact, this entire point is what we're doing is for loops. Okay, now, first of all, part one. This is a circuit. Okay, A, B, C, D, E, F, G, and back to A. Apply KCL to find an equation connecting I1, I2, and I3. Okay, so I think it makes sense that I1 should equal to I2 plus I3. That's fairly easy. Now, they've said in part 2, apply KVL to loop A, B, C, D, E, H, A. Now, what the hell is this? Why are we, going back to nursery class? Even that is wrong. So, A, B, they're talking about a loop and they will generally give you a loop to figure out. Okay. Now, check this out. A, B, C, D, E, H, A. Right? They are talking about a very specific loop in this case. They're asking you to apply KVL according to this loop, this one. Okay. So, how do you apply KVL? You remember what was KVL? Sum of EMF is equals to sum of potential difference in a loop. They have defined the loop for you, right? Now, what are the EMFs in my loop? It's just one E, right? E. What are the potential drops in my loop? The potential drop, one of them was this one, right? It was equal to IR1, I1 R1. Make sure to keep the subscript, be careful about it. Then, was there any other drop in this loop? Yes, there was, right? It would be I3 R3. It would be I3 R3. That's it. You've used KVL. That's how we use Kirchhoff's voltage law. Now, they've given a weird loop over here. HGFEH. Check it out on the loop. Where is HGFEH? HGFEH. They're talking about this loop, right? They're talking about this loop. This seems weird. This isn't even the direction of the current, which is important. Again, write down sum of EMF. Okay. Yep. So sum of EMFs is equals to sum of potential drops, right? Now, what is the sum of EMFs in this case, in this loop? Do we notice any batteries in the loop? I don't, which means that EMF is actually going to be zero in this case. Do we notice any potential drops? I do, I2, R2. But notice something, this is important. Notice, write this down. Notice that the loop is actually in the opposite direction of the current. So that means when you write I to R2, you are going to attach a negative sign to it. So rather than writing I to R2 as a potential drop, I'm going to write negative I to R2 as a potential drop, right? Then going forward with the loop, A, G, F, E, H. Now, because from E to H, there is a drop of I3, R3, then I can very easily say it would be positive because it's in the same direction as the loop. So plus I3, R3. Okay, sounds good. And what else? Yep. And that's it. You have used Kirchhoff's voltage law in this scenario as well. I've written it over here, right? If I'll write it down. If I is in opposite direction of loop, okay, is opposite direction of loop, use negative voltage or negative IR. Okay, so that's the rule. We'll do multiple examples to make it more clear, right? And another thing, if the battery is in direction of the loop, then it will be E. But if, for example, if he made the loop start like this for the first part, then it would actually be negative E. Okay, it'll become clearer in a few examples. Yes. Any questions right now? So I am careful with it in the next ones. Please bring up questions because I'm sure you will have questions. I never got this the first time. No? Did you get it?
So I'm still reading. Just 1 second.
Okay, okay, sure.
Sir, I have a question.
Yes.
How do we identify that if it's a loop or not? Like,
Hmm.
is it the shape or?
So they will give you letters to identify the loop, right? So this is given in the question. H, G, F, E, H, right? That means you start from H, H, G, F, E, H. So they're talking about a specific loop. A, B, C, D, E, H. They are giving you the letters to walk you through which loop they're talking about.
Okay, so like for the HGFEH,
Hmm.
how was the EMF before like zero?
Because according to Kirchhoff's voltage law, the sum of EMFs should equal to the sum of potential difference in a loop, right? So that means in this loop, if you try to apply Kirchhoff's voltage law, do you see any EMFs, any batteries in this loop? No, right? So that
Yeah.
means if there are no batteries in this loop, then the left side of the equation would be zero, right? And now, are there any potential drops in the loop? Yes, there are. It's I2 and R2, right? Now, I2 and R2 is actually opposite direction of the loop, which means this is going to show up as a negative sign, right? And then because EH, EH is actually in direction of the current, so that means it's going to show up as a positive value. Now check this out, check this something interesting. If I take I2, R2 on the other side, this becomes equal to I3, R3. And what does this tell me? Do you remember that in parallel circuits or in parallel, junctions, both of these get the same voltage? By that same principle, then this voltage and this voltage would be same, right? And that's proven, right? That if you use Kirchhoff's voltage law, then that means the voltage drop in the first resistor and the voltage drop in the second resistor would be equal, according to Kirchhoff's voltage law. So it's another way to kind of like prove it. Does that make sense or no?
Yeah, I got it.
Yes. Okay. When you solve more question, it becomes clearer. Now, check this out. Use Kirchhoff's laws to find the current in the circuit. Now, check this out. You have multiple cells to get attached together. Now be careful of the sign, right? This is why we did the EMF combinations. Positive, negative, but positive, negative. But this is negative and positive and negative and positive. Okay. So 6 volt and 2 volts, they're attached to each other. By the way, this is like 1 6 volt and this is another 2 volt. Okay. So they've identified the loop for you in this case, by the way. They've already told you that, take this loop like this. Okay, so I don't think so. We need Kirchhoff's current law. We will need Kirchhoff's voltage law over here. So KVL, it says it says that the sum of EMFs is equals to the sum of potential difference across any loop. You can choose the loop, by the way, right? So what are the sum of EMFs? It's actually going to be 6 minus 2 because positives are connected with, sorry, negatives are connected with negatives. What is the potential drop? It would be 10 times I, right? I'm using IR, right? IR. So I times 10 plus I times 30. So 30I plus 10I. Then according to that, this becomes 4 is equals to 40I. So that means I is equals to, oh, wait 1 second. Oh, right. I is equals to 0.1 ampere, right? So this is just a basic application of Kirchhoff's. voltage law. It's not complex at all. It's just very simple, right? It becomes it. You could have done it with Ohm's law over here, but in certain situations, Ohm's law it falls, it dies, right? For example, like this. Can you try to solve this? I would like you to try, like take 2 to 3 minutes to try to figure out this question. Try to find I1, I2, and I3. It's a good one. How the hell are you even supposed to use Ohm's law over here? It seems pretty weird. These are like two batteries weirdly connected. And I don't know what is the voltage across the 30 ohm, and I don't know what is the voltage across the 10 ohm. It seems horrible to solve this kind of question using Ohm's law. Ohm's law has failed. It has failed us. Yes. Any ideas, anyone? Yes, Ariz. Are you here? Oh.
Yeah, I'm there.
What do you think, Ariz? How do you do this question?
I'm not really sure, to be honest, but I'm just trying something out.
Okay. Yes. Kaima, any ideas?
I'm still thinking.
I'm not sure if I'm correct,
Hmm.
but would I1 be 0.15, I2 be 0.067, and I3 as 0.217? I'm not sure though.
Hmm. I don't know. Maybe, but I don't think so. That's the answer. What about you, Anya? Any idea?
No, I'm completely lost.
Okay, let's see. So in this case, first of all, try to first apply KCL. Okay, because that seems pretty straightforward to do. Current law. Can I relate the current somehow together? I can. I can say that I3 is equivalent to I2 plus I1, right? That's pretty basic to say because the currents entering over here are leaving from I3. Now, I've made an equation for I3. How can I apply KVL? Keep in mind that you can use KVL no matter how you want it. Okay. Now, what does that mean? That means you can use any loop, and then if you just add it up in some weird way, then you can say that then you can very conveniently say that you've done it right. How? Now check it out. Can I choose this loop and apply KVL to that, right? I'm choosing this loop. I'm picking loops, right? It's okay to pick random loops. I can choose this as a loop. I can choose this as a loop. I can choose this as a loop. I can also choose, like whatever loop you want. So for example, let's say I choose this loop, this one. Okay. Now in this loop, let's call this loop A. So for loop A, do you see that the sum of EMFs, the sum of EMFs is actually equal to sum of potential difference in any loop? Remember that. That's Kirchhoff's voltage law. What are the EMFs in this loop? It's 6 volts. That's it. What are the potential drops? It is I3 times 30 plus, notice that across the 10 ohm resistor, it's actually 10 ohm. So that's going to be I1 times 10 ohms. Okay, but that's a problem. I don't know both of the currents. That's problematic. Okay. Now, check it out very carefully. Can I use this equation to somehow substitute I3 or I2 over here? I can, right? So that is one way to do it. Let's check it out. Let's see if I'm successful in doing that. So for example, if I were to, no, but that's a problem because that'll then bring in I2, right? If for example, if I have to substitute I2 with this over here, then that'll bring in another unknown I2. Okay. Now, how about we make another loop, right? Because that's somehow we could cancel out stuff. For example, loop B. For example, let's choose this loop. Let's choose this loop B, right? Now loop B. Let's see what that is going to give me. For loop B, I am checking again, sum of EMFs. Sum of EMFs is equals to sum of potential drops, right? Now, what are the sum of EMFs? 2 volts. What are the potential drops? It's only just one. 30 multiplied by I1. So 30 into I3, sorry. Oh, that's it. I have figured out I3, right? I have figured out what I3 is, right? Because according to this loop, there is only one potential drop, which is this 31, right? This 31 has I3 going through it. So that's pretty easy, right? Now let's check it out. So how about I substitute 2 volt over 30 is equals to I3? Oh, I fixed the problem. So I3 is actually equal to 2 over 30, which is going to equal 0.067 ampere. This is going to show up everywhere now. Okay. Okay. Now I figured out I3. If I figured out I3, can't I just plug this in over here and find out I1? I can. It's pretty easy. 6 volt is equals to 0.6, no, 0.067 into 30 plus 10i, right? So let's find it out what it is. So 6 minus 0.067 divided by 30. No, wait. It was subtracted into 30. We're 10. Okay. So that means I1 came out to be 0.4 ampere. Great. So I1 came out to be 0.4 amperes. Now what else? What else? Oh, we figured it out. So we've already have figured out I3, we've already figured out I1, and we already have the equation that connects all three of them. So you can figure out I2 using that. So I3 minus I1 is equals to I2, right? Now, what was I3? I3 was equal to 0.067 minus 0.4, which is going to give me 0.067 minus 0.4, which is giving me minus 0.33 amperes, and that is I2, right? This is going to give me I2. So that's how we figure out all I1, I2, and I3, right? So congratulations, we have figured it out. And by the way, the negative current is slightly difficult to explain, but if you're getting a negative current, that's okay. although you will never get it, but this is like a very specific example where you got a negative current. Okay, but like you can assume that you will almost never get a negative current. If you do get it, that's okay. You can write it down as a negative one. Okay. Okay, sounds good. Okay. Yes, Hania, does it make sense at all or no?
No, I get it now.
You get it? Okay. Moving on. We'll do one more question and then we'll stop. Okay. Now, let's check it out. For example, back, let me erase this first. Oh, what happened? Oh, I lost the diagram. Shit. Okay. Try this one. Try to apply KVL. Now, this will be impossible to solve with Ohm's law, right? You just want to make up a single equation that connects all the EMFs and the voltages together. In fact, this is just like a single loop. This is a loop from a very complicated circuit, as it says, right? So it's kind of like it's a part of a very complicated electronic circuit, and that's why they're just asking you to use KVL in this case, right? Be careful of the current directions and the EMFs. Try to apply it, and then write down the equation. Yes, Anya. Any idea? Have you made a loop, Kaima? Were you able to come up with an equation?
I tried making one.
Hmm.
What I did was I
Hmm.
kind of like directly applied the KVL. I used like the whole thing as one loop.
Okay. Okay, that's fine.
And yeah, I added all the like the
Okay.
all of the E's, and then
Hmm.
I tried doing like the I times R. But I wasn't
Uh-huh.
sure with my signs because like the direction of the
Okay.
current in some of them
Yes,
is
absolutely. Let's check it out. So if I were to apply KVL, right? So sum of EMFs is equals to the sum of potential drops. Now, you can choose any loop. You can choose it like this or you can choose it like this, right? But just be consistent with it. So let's say I choose this loop. Okay. Now, that means I'm taking this to be my flow of current. Okay. Now, so that means I'm taking my loop to be like this. Okay. So what are the EMFs? First of all, notice the EMFs. It is E1 and E2 are going to add together, right? Because positive is connected with negative. So E1 plus E2. What are the other EMFs? E3. Now notice E3, the positive is connected to the positive. So that means you're actually going to subtract it. E3, right? Is there anything else? No, that's all the EMFs. Then what else? What are the potential drops in this case now? The potential drops are actually, so notice which potential drops are with your loop and which one are against it. Okay, now try to be try not to worry about the current so much, right? Like don't figure out, where is this current going, where is it coming from. If it's going, it's going. We can't do anything about it. We can just see whether it is aligning with our loop or it is not. That's it, right? If you try to break down currents into series and parallel and junctions, it's going to become very difficult for you to solve it. Okay, now potential drops. I just see one I, one R1, right? What else? Now I to R2 is actually in the opposite direction. Current is going in this direction, right? So it's actually going to minus I to R2, right? What else? Now I to R3, it's actually going to be in the opposite direction as my loop. So it's actually going to be minus I to R3. Then what else? R4, I1 is just in the same direction as my loop. So it's going to be I4, no, sorry, I1, R4. And that's it, right? So this is the loop that would be made for Kirchhoff's law. They could ask you to specifically write this expression, right? So don't take this lightly. They can give you exactly this kind of question, then they could give you exactly this question that make a loop for it. Okay. So yes, Hania, did you get it right or no?
I did, but except for E3, I wrote it as positive.
Yes, that's why you've got to be careful, right? Because if you bring it down, this positive is connected to this positive, whereas it should be the opposite, right? Its positive should be connected to negative. So that's why this is going to be negative. Okay. So yes, Kaima, does that make sense? Any questions?
No questions.
No. Okay. Okay. Sounds good. You can try question number 6 by yourself. Okay. I would recommend that you try it yourself before we do it in the next class. This is a good one. Question 6 is a good one. It's like a two-part question. We've got question 6 and then we've got question 7 and then 9. We'll do all of those in the next class. Right? Try this yourself before class. Okay. If you don't get it, of course, we will do it, but I would recommend that you try it yourself and then we will definitely figure it out. Don't spend more than 5 minutes on it, on each question. If you're able to solve it, great. If you're not, then of course we'll do it. But you'll have a better idea of what not to do when you solve the question. Okay. RS has also left. So let's stop here and resume on Wednesday. Okay. And Hania, how are you prepping the rest of your syllabus?
In terms of subjects or
Yes. No,